In our previous presentation, we understood how to find the time complexity of single loops where in the update expression, the variable is divided by a constant. Now in this lecture, we will understand how to find the time complexity of single loops where in the update expression, the variable is raised to the power some constant. So let's get started and let's see what are the topics of this lecture. The first topic of this lecture is single loop update expression with power. In this topic, we will understand how to find the time complexity of single loops where in the update expression, the variable is raised to the power some constant. After this, I will propose the homework problem of this lecture, which you need to solve on your own. So these are the topics of this lecture. Let's get started with the first one, single loop update expression with power. Let's now understand how to find the time complexity of single loops where in the update expression the variable is raised to the power some constant. Let's say this is the for loop, and in this for loop we can observe variable I is initialized to 3. This is the initialization statement. After this, the conditional statement is I less than or equal to n. Then the update expression is I equal to I square. This should be the focus of this loop, I equal to I square. As mentioned, we want to find the time complexity of the single loop where in the update expression, the variable is raised to the power some constant. We can observe the variable I is raised to the power 2 in this update expression. And in this for loop, we can observe the printf function, and this printf function will print Neso Academy when this loop will run. Now, what's the time complexity of this loop? We already learned in our previous lectures how to find the time complexity of a loop. The time complexity of a loop is same as the frequency count of the innermost instruction of the loop. In this loop, we can observe this is the only statement which needs to be executed, and therefore this is the innermost instruction. The frequency count of this instruction is same as the number of times this instruction will execute. So, in order to determine the time complexity of this loop, we need to determine how many times this statement will execute. How do we find this? In order to find how many times this instruction will execute, we need to analyze each iteration of this loop. In each iteration, we need to carefully observe the value of I. We need to observe the pattern in different values of I, and this will give us the number of times this statement will execute. And eventually, we will get the time complexity of this loop. So let's do the analysis. We know the initial value of I is 3. So in the first iteration, value of I is 3. After this, 3 is compared with n. Can we say 3 is less than or equal to n? Let us assume that 3 is less than n. N is some large value. Therefore, this condition is true, and hence, this statement will execute. After this, I is updated to I square. As I is updated to I square, we know the current value of I is 3. Therefore, I is updated to 3 square. So in the second iteration, we got this value of I, which is 3 square. After this, 3 square is compared with n. Let's say 3 square is less than n. The condition is again satisfied. Again, the printf function is evaluated and update expression is evaluated. After evaluation of this update expression, we will get 3 power 4 as the result. Because 3 power 2 is the current value of I, we now need to take the square of 3 power 2. This means now we need to multiply this power 2 by this power 2. 2 times 2 is 4. So we will get 3 power 4 as the value of I in the third iteration. We can write 3 power 4 as 3 power 2 power 2. So instead of writing 3 power 4, let's write 3 power 2 power 2 because 2 power 2 is 4. We can observe some pattern here. After this, again this condition is checked. Let's say this condition is satisfied. Neso Academy is displayed. Then update expression is evaluated. We again need to multiply the power by 2 because of this update expression. 2 power 2 is 4, and if 4 is multiplied by 2, we will get 8. So we are getting 3 power 8. Let's represent 3 power 8 in this form. We will get 3 power 2 power 3 because 2 power 3 is 8. So in place of writing 3 power 8, we can write 3 power 2 power 3. I'm writing in this form because we can observe the pattern now. We can observe the first value of I is 3 power 2 power 0. 3 can be written as 3 power 2 power 0. Similarly, we can write 3 power 2 as 3 power 2 power 1. In the second iteration, we have 3 power 2 power 1. Then we have 3 power 2 power 2. After this, we have 3 power 2 power 3. This will continue up to, let's say, 3 power 2 power k. Every time we can observe 3 power 2 is the constant and the power of 2 is the only factor which is changing. Here we have 2 power 0, here we have 2 power 1, here we have 2 power 2, here we have 2 power 3. So we are assuming here this is the last value of I for which this condition is true. And the power of 2 in this case is k, some k. We don't know what this k is. So this is my assumption that 3 power 2 power k is the last value of I for which this condition is true, and hence 3 power 2 power k is equal to n. Let's say this is my assumption. So with this, now we know 3 power 2 power k is equal to n. But eventually, we want to know how many times this statement will execute. The answer lies within this pattern only. We can observe in this pattern that in the first iteration we have 3 power 2 power 0. So in the iteration number 1, the power of 2 is 0. Similarly, in the iteration number 2, the power of 2 is 1. In the iteration number 3, the power of 2 is 2. In the iteration number 4, the power of 2 is 3. Can you observe the pattern here? The power of 2 is always 1 less than the iteration number. If we are in the iteration number 4, then the power of 2 is 3. If we are in the iteration number 3, then the power of 2 is 2. If we are in the iteration number 2, then the power of 2 is 1. Similarly, here we have 2 power k. If we know the iteration number of this value of I, then it will give us the number of times this statement will execute. Why? Because we are analyzing each iteration of this loop, and this is the last value of I which we are assuming for which this condition is true. This means this is the last iteration of this loop. If we know the iteration number of this value of I, then it is equivalent to the number of times this loop will run, and this is equivalent to the number of times this statement will execute. We know the power of 2 depends upon the iteration number. The power of 2 is always 1 less than the iteration number. Here we have k as the power of 2. Therefore, the iteration number for this value of I must be k plus 1. So k plus 1 is the iteration number for the last value of I for which this condition is true. And hence, this loop will run k plus 1 times. And this means this statement will run k plus 1 times. So now we know this statement will run k plus 1 times, but this is not enough. We need to determine the time complexity in terms of the size of the input, which is n. This is the assumption. So if we want to represent time complexity in terms of n, then writing time complexity in terms of k is not the solution. We need to represent k in terms of n. Eventually, this will give us the time complexity. So it is not enough to say this statement will execute k plus 1 times. We need to represent k in terms of n to eventually get the time complexity. We assumed that 3 power 2 power k is equal to n. So this equation will help us in finding the time complexity of this loop. We need to now find the value of k in terms of n. Let's do this now. Let's solve this equation. In this equation, we can observe in the left-hand side we have 3 power 2 power k, and in the right-hand side we have n. If we take log on both sides, then 2 power k will come in front of logarithm. And if we again take log on 2 power k, we will get k in front of log. So eventually we would be able to find the value of k. Let's apply log on both sides for the first time. Let's apply log base 3 on both sides. The reason is, here we have constant as 3. If we take log base 3, then eventually we will get log 3 power 2 power k base 3. 2 power k will come in front of log 3 base 3, and log 3 base 3 is 1. It is easy to find the value of log 3 base 3. We know log a base a is always 1. And applying log will also bring 2 power k in front of logarithm because of the property of logarithm, log a power b base c. Log a power b base c is equal to b times log a base c. So this power will come in front of logarithm. This is what we already know. So let's take log base 3 on both sides. After applying log base 3 on both sides, we will get log 3 power 2 power k base 3 in the left hand side and log n base 3 in the right hand side. Now what is log 3 power 2 power k base 3? It is equal to 2 power k times log 3 base 3 because of the property of logarithm. Log a power b base c is equal to b times log a base c. We are applying this property. So we will get 2 power k times log 3 base 3. What is log 3 base 3? Log 3 base 3 is equal to 1 because log a base a is equal to 1. So eventually we will get 2 power k here. Now I hope it is clear why I took log base 3 here. Because I want to eliminate this constant. And eventually I want to bring 2 power k to the base. So from this we will get 2 power k equal to log n base 3. Now we want to know the value of k, not 2 power k. 2 power k is equal to log n base 3, but we want to know what is k. In order to bring k to the base, we can again take log on both sides. This time we will take log base 2 on both sides because here we have the constant 2. Let's apply log base 2 on both sides. After taking log base 2 on both sides, we will get log 2 power k base 2 in the left hand side and log n base 3 log base 2 in the right hand side. What is log 2 power k base 2? K will come in front of log 2 base 2 and log 2 base 2 is 1, so we will get k here. So we can say k is equal to log n base 3 log base 2. So this is the value of k. K is equal to log n base 3 log base 2. And we know this statement will execute k plus 1 times. And we know k is log n base 3 log base 2. So we can replace k by log n base 3 log base 2. We will get log n base 3 log base 2 plus 1. These many times this statement will execute. So this is the frequency count of this instruction. And we know the frequency count of this instruction is same as the time complexity of this loop. We represent time complexity in asymptotic notation. Let's use theta notation to represent time complexity. We can write log n base 3 log base 2 plus 1 as theta of log n. We do not have to worry about constants and we do not have to worry about bases when we write in terms of asymptotic notation. So this is theta of log n. This is the time complexity of this loop. I hope now it is clear how to find the time complexity of these type of loops. Now here is one more loop. Let's say we need to determine the time complexity of this loop as well. We can observe I is initialized to n. Then after this, the condition is checked. Is I greater than or equal to 5? Then the update expression is I equal to square root of I. Here we have square root of I. Again, this is I power something. Here in the power we have 1 by 2. We can observe the variable is raised to the power some constant. Hence, this is the update expression with power. Now let's determine the time complexity of this loop. In order to find the time complexity of this loop, we will follow the same process. We will analyze each iteration of this loop, and this means we will analyze each value of I in each iteration. Let's do this. In the first iteration, we have I equal to n. In the second iteration, we will be having n power 1 by 2. So in the second iteration, the value of I is n power 1 by 2. What about the third iteration? In the third iteration, we need to multiply 1 by 2 by 1 by 2. Because we need to take the square root of n power 1 by 2. And this means we now need to multiply 1 by 2 by 1 by 2. This gives us 1 by 2 square. So now in the power of n, we have 1 by 2 square. This is the third value of I. This means in the third iteration, we have this value of I. Then we know what's the next value. The next value will be n power 1 by 2 power 3. And we can observe the pattern here. The first value of I is n power 1 by 2 to the power 0. Then we have n power 1 by 2. Then we have n power 1 by 2 square. Then n power 1 by 2 cube. And this will continue up to, let's say, n power 1 by 2 power k, where k is some value which we don't know. And I'm assuming n power 1 by 2 power k is equal to 5. So this is the last value of I for which this condition is true. After this, I will be less than 5. So n power 1 by 2 power k is equal to 5. Now, from the previous example, we already know if we determine what's the iteration number of this value of I, then it is equivalent to the number of times this loop will run, or in other words, the number of times this statement will run. In the first iteration, we have n power 1 by 2 power 0. The power of 1 by 2 is 0 in the first iteration. The power of 1 by 2 is 1 in the second iteration. The power of 1 by 2 is 2 in the third iteration. The power of 1 by 2 is 3 in the fourth iteration. So one thing is clear, that the power of 1 by 2 is dependent upon the iteration number. And it is always 1 less than the iteration number. In the iteration number 4, the power of 1 by 2 is 3. In the iteration number 3, the power of 1 by 2 is 2. Similarly, in the iteration number k plus 1, the power of 1 by 2 is k. So this is the value of I in the k plus 1th iteration. Hence, this loop will run k plus 1 times, and this means this statement will run k plus 1 times. Now we need to determine the value of k in terms of n to find the time complexity. Let's do this. We know n power 1 by 2 to power k is equal to 5. Let's now solve this equation. We need to find the value of k. This means we need to bring it to the base. We can do this by taking log on both sides. Let's take log on both sides. Here we have value 5. So let's take log base 5 on both sides. Here we are getting log n power 1 by 2 power k base 5 in the LHS. And in the RHS we are getting log 5 base 5. Log 5 base 5 is 1. And here we can apply the logarithmic property log a power b base c. Log a power b base c is equal to b times log a base c. So we will get 1 by 2 power k times log n base 5 here. So we can rewrite this equation as 1 by 2 power k times log n base 5 equal to 1. We can bring this 2 power k in the RHS. We will get 2 power k equal to log n base 5. Now we want to bring k to the base. Again, we need to take log on both sides. This time we will take log base 2 on both sides because here we have the constant 2. Now let's take log base 2 on both sides. We will get log 2 power k base 2 in the left hand side and log n base 5 log base 2 in the right hand side. This is equivalent to k. So this equation is equal to k equal to log n base 5 log base 2. So this is the final value of k, and we know this statement will run k plus 1 times, and the value of k is log n base 5 log base 2. So this statement will run log n base 5 log base 2 plus 1 times. And this means the time complexity is once again theta of log n. After eliminating the constants and after eliminating the bases, we are getting this time complexity. So theta of log n is the time complexity of this loop. So in this way, we can find the time complexity of single loops where in the update expression, the variable is raised to the power some constant. So with this, we are done with this topic. Now let's move to the homework problem. Determine the time complexity of the following loops. These are the loops, and your job is to determine the time complexity of these loops. Not only this, I want you to post your answers in the comment section as well. So we are done with the topics and we are done with this lecture. Okay friends, this is it for now. Thank you for watching this presentation. I will see you in the next one.